Okay, guys. So I just want to continue where we left off with our last video. So we're talking about this idea of going around the turn unbanked, at a banked turn perfectly smooth. And the reason you can do that is because there is a component of this normal force which provides a centripetal force. So if you notice in this picture right here, you've got your car going around a banked turn. Okay, it's kind of driving into the screen. And the normal force is coming up from the road perpendicular. And then if you take that normal force and break it into a vertical and a horizontal component, it's this horizontal component right here which supplies the net force, which we're going to define it as, right here, it's looking like n sine of theta. We're also going to define it as mv squared over r, which is our centripetal force. So in this picture right here, notice that you take your two components. Your net force in the x is being provided by that sine component of the normal, which is equal to mv squared over r. And then your vertical component is in equilibrium with weight. So this cosine component of normal, we equal it to mg. And really this triangle that's created now, which has an adjacent side of mg and an opposite side of mv squared over r, is how we solve these problems. You can look at a triangle and just say the tangent of theta equals mv squared over r divided by mg, and your m's cancel. So I've got two problems to figure that out. Answers are down here, and then you're going to want to go ahead and check out number 13a and 13b in your practice set and work through those concepts. There is also a extra credit problem right here. I'm not going to go through this problem here. I want you to work it out. It is extra credit, and notice right here that this is a banked turn with friction. So it's the same as the last problem, but now you're adding in these components of friction. Okay. You can go ahead and work on the extra credit for that. Next one, tetherball. So this is a situation in physics that we look at called a conical circular motion situation. A couple fun videos to watch. And then you want to check out this situation here with the conical pendulum. So just like tetherball goes around, and you're going to go ahead and look at the components of the tension. I could look at this cosine and the sine components and realize that the horizontal sine component is actually equal to the mv squared over r, or the net centripetal force that's keeping it in a circle. And the vertical component right here is equal to mg, or the weight. Now, once I realize that that triangle is set up, now I deal with triangles as I always would in a math class. I've got all the answers to work out these questions, but again, it's really just getting into breaking up and doing some trig. So there's problem number 11 to help you with that one. Next problem, there's a fun video to watch, the Vomit Comet. Go ahead and check it out. And then we're going to look at this idea of vertical circular motion. Now, with these types of problems, we're looking at like going around like a Ferris wheel. Notice that whenever you're going around on this Ferris wheel right here, you always have mg pointing down. Okay, but there's a support force on this Ferris wheel. It could be something just like a normal force for like a ball on a string. It might be tension, but notice that this support force is centripetal and it's always directed inwards. Okay, well, if I switch that. And now when I look at my net force expression, net force is going to be the centripetal force. Okay, that inward directed centripetal force is equal to the combination from a free body diagram of the support, in this case it's normal, plus mg in this case, because we're at the top. So notice that the support force and mg are both facing the same direction, and so that's why I'm adding them together. There's a problem to work out here. You can do the same thing at the bottom, but in this case, notice that your support is going up, your your weight's going down, and so you can go ahead and work it this way. And in another circumstance that we have here, we have the question is, how fast would you go before you start to fall off of this in a loop-to-loop, like on a roller coaster? And when you're about to fall, your normal gets to 0. So we kind of manipulate the math that way too. A couple more problems to work through. Then there's some Khan Academy exercises. Then you fill out the daily attendance form, and we're all done. So that's our lesson for today. So good luck, everybody. If you have any questions, ask on the fact sheet. If you want to have a meeting, go ahead and make an appointment on the fact sheet. Have a great day, everybody. Goodbye.